Morning. It looks like we have about 12 people here so far. Since it's the first time we're doing this in Zoom, I'm just going to wait a couple of minutes for more people to join. Today, MECH 205, we are covering Boolean logic. So that would be covering slide decks 1.4, 1.5, 1.6, and 1.7. Boolean logic is the backbone of automation, backbone of computing. It's a decision-making process. Moving forward in your labs, you will start doing relay logic. You need Boolean to really create these to solve real-world problems. We need to be able to decide what to do, what an output should do, and we do that based on information on the inputs. This is suitable for Boolean logic. So previously, last week, we covered that binary numbering system. Okay, 1 or 0. It's like the Boolean decision process. I'm going to have an output. I'm going to make a decision. It's going to be do one thing or another. Now, if I've got 4 possible outputs, usually I pose the question so that I will eliminate 1 or 2 of the possible outputs. And then I pose a second question, a third question. So we have successive decisions that we ask ourselves, and we find the answer to move towards the decision. So when we say that there's only 1 possible or 2 possible outcomes, well, that's by breaking it down and asking the appropriate questions. The hardest part about Boolean, using Boolean to make a decision, is to pose the questions properly, to interpret the real world, pose the questions in such a way that they can be answered either just true or false, yes or no. This is why when we talked about digitization compared to an analog system last week, it was important to digitize. It allows us to more easily pose a good question to get a simple answer, yes or no answer, and then move on in our decision-making process. So the first slide deck, 1.4, we're going to talk about 3 gates, 3 logic gates, or 3 decision types. I'll just share my screen and get started. So slide deck here, 1.4 out of content. The reference material from the textbook would be from chapter 4, where you could read more about this. I do go over it slightly different to how the book presents it. So the book makes a good alternative if you need just a second point of view on how to do these things. So logic. The foundations of this give us the ability to make logic-based decisions based on the data available. Okay, Boolean algebra is a relatively simple mathematics form based on having just 2 states, trues and falses, or highs and lows, or zeros and ones. We use it to describe an output state based on a series of inputs. Based on a series of inputs and decisions, we can arrive at an output or a decision. Now, the Boolean mathematics part has been around for a couple of 100 years, named after Charles Boole's. But there's evidence that this sort of thing has been used for thousands of years in many cultures. If we look at it, a Boolean is basically how we use a search engine for on the internet. When you type in a search, you're searching for a parameter, it's going to spit up a whole bunch of results based on some Boolean logic. As you would have all seen, the better you are at describing what it is you're looking for, the better your results will be. This is where I come to the point of naming or developing good questions, good decisions in order to get good outputs, good logic. Now, the first thing we're going to look at is a truth table. It can describe a function of a digital device. It shows all the inputs and all the possible outputs. These can be very useful. I use them all the time, even around the house. Like I'm putting in some new lights or a new motion detector or something like that. I'm going to look at all the inputs and see what the outputs are. And once I've done that, then I develop the logic to generate the outputs that I want. So basically, we see that there's 2 parts to this truth table. There's all the possible inputs. Now, considering I've only got zeros and ones as inputs, and I know my binary, if I've got two inputs, 2 squared means 4 possible sets of inputs. If I've got 3 inputs, 2 to the power of 3 gives me 8 possible combinations of inputs, etc., etc. And then I would write down the outputs that I want. So at the moment, I've done no design, I've done no math. All I've done is create a truth table of my desired outputs as a result of every possible input. Now, when I develop a truth table, often I have X's. An X meaning I don't care. Okay, so this helps simplify my truth table. I can get rid of those inputs and outputs. I don't really care if the light is on or off in certain conditions, so I'll often ignore that. And I don't care if the light's on or off. Of course, that wastes energy, so usually I don't have any X's in my process by the time I'm finished, by the time I consider all the aspects. But to get a machine up and running, often there's a bunch of things I don't care about, I ignore. But in the end, by the time I've got a fully complete comprehensive program, those X's are gone. I've got just zeros and ones to make my decisions. So we can make our decisions based on 3 what we call primary functions. And, okay, the first one being and. I look at one input and I look at another input in order to make my decision. So I say, if I am thirsty and there's a beer available in the fridge, I might drink a beer. Okay, so it's an and. Both have to be available, both have to be true in order for my output to be true. Both my inputs must be high for my output to be high. I can have an or function where only one of 2 things needs to be true. Okay, if I want a beer or it's warm outside, I'll go and have a beer. Okay, it's not great. If I want a beer or it's warm outside and I don't want a beer, doesn't really matter. I want a beer and it's cold outside, doesn't really matter. It's just an or statement. If one item is true or the other item is true, the output is true. So consequently, both the inputs would have to be false for the output not to be true. Okay, and then the third basic one is a not, just an inversion. We invert the decision. Is it light outside? No, it isn't. Okay, shall I turn on the lights? Okay, we just invert. So if it's light outside, we don't turn on the lights. If it's dark outside, we turn on the lights. We just invert the process. So these are your 3 basic primary functions, and everything can be built from these 3 primary functions. It's not a very efficient way of necessarily doing it with these 3 basic functions, but it is possible to do this. So certainly when I get something like a pneumatic computer or something like this, typically I'm using pretty much just these 3 ands, ors, and nots. The other ones we'll talk about later are far too complex in a pneumatic system, very expensive. So every decision can be really made on these ands, ors, or not in successive decisions. So for this and, all the inputs must be true for the output to be true. Okay. So I might actually have 3 inputs or 4 inputs or 5 inputs. Okay, and. Okay, so input 1 and input 2 and input 3 and input 4 all have to be true in order for the output to be true. So other ways we can talk about this. If all the inputs are 1, the output is 1. Conversely, if any of the inputs are false or 0, the output must be false or 0. Okay, so an and, all the inputs must be true in order for the outputs to be true. Now in North America, we tend to use this symbol for an AND gate. And I just remember it looks kind of like a D. If any of the inputs are true, we have an output that is true. So this is a symbol that we would use in our schematics to represent an AND gate. So I've got an example here. If the inputs is 0 and 0, anyone like to guess at what the output would be?
0.
0, yeah, simply 0. If any of the inputs is 0, the output must be 0. A 0 and 1, the output, of course, would be 0. If any of the inputs is 0, the output would be 0. A 1 and a 1, well, If all the inputs are 1, the output would be a 1. So this is the truth table for that AND gate. If I look at the inputs, wherever there isn't a 0 available, 1 or 2 zeros, doesn't matter, available as an input, the output is going to be 0. The only time an output is a 1 is every input is a 1. So that's the basic truth table for this AND gate. They can have multiple inputs, which has got examples here, 3 inputs, 5 inputs. Same rules apply. If any of the inputs is a 0, the output is going to be a 0. Now the international symbol, the IEC symbol, is this square box instead of that D-looking shape with an ampersand in it. Okay, so that's fairly easy to remember. That's an AND when you see that. You do need to know both. I tend to use the North America ones a bit more because we're in North America. But you will be using international symbols. You will be using machines from around the world. You will need to know these international ones as well. So that's the symbol, but we don't always use symbols. We often want to be able to write things down. I want to be able to scribe this Boolean logic. I want to be able to write it quickly on a postage stamp or on a computer. We're going to use the dot as a symbol for AND. Okay, you may have used this in school as a multiplication symbol. It gets a little confusing because when you were at school, you learned 2 and 2 equals 4. You learned it, or 3 and 5 equals 8. You learned it as an addition. You often use the word AND when we're adding, whereas really it's like a multiplication. If I think about those inputs, if I multiply them together, say I've got 3 inputs, I'm going to look at input 1, 2, and 3, and say they are 1, 1, 0. I go 1 times 1 times 0 equals output of 0. So it works very much like a multiplication, and that's why we use this dot as a multiplication form. Or we can just skip it all together, and if I have 2 inputs stuck together, I read it as A and B equals X. Okay, so often similar to multiplication, because if I put zeros and ones on those inputs, I can multiply them together to get the output. Okay, so this is just for this symbol, this AND symbol. The OR function, if any input is true, the output is true. Okay, wouldn't that be great? Hey, if it's anyone's birthday today, we're going to go to the bar and celebrate. Okay, whereas if it was and, hey, if it is whose birthday, who we got here today, if I was to say, listen, if it's Aaron's birthday and Alex's birthday and Ahmed's birthday and Cindy's birthday and Darren's birthday and Jacob's birthday today, I'm buying. Yeah, it's a really unlikely thing to get everyone's birthday, so it's a less likely event. Whereas ORs, only one of the things would have to be true, and we've got an output that would be true. So ORs, I'm looking for anything. So if any point along the Bow River, the water gauge gets to 1 meter above flood level, they may have a certain alert system. If it gets to 2 meters above flood level, something else is going to happen. Okay, we're not going to wait for every point along that river to be approaching flood level. So ORs have a very different use than ANDs. If any of the inputs are true, the output will be true. The symbol, I just remember it's not the D, so it must be the OR statement. Okay, this one with a curved back, a bit of an arrowhead. Once again, inputs on the, typically we draw this inputs on the left. They don't have to be, it's just typical. Outputs on the right. There is only ever one output. Okay, with all these logic gates, there is only ever one output on a single gate, but you have multiple inputs or can have multiple inputs. So if any input is a 1, the output's going to be 1. If all the inputs are 0, then the output is going to be a 0. So I've got a logic gate here. It's an OR gate. I've got 0 or 0. The output is going to be a 0. 0 or 1. The output is going to be a 1. 1 or 1. The output is still going to be a 1. So we've generated a truth table for ORs. You notice here, if any of the inputs are a 1, you can see there that that output is a 1. Okay, so only time an output is a 0 is when all those inputs are a 0. Once again, you can have multiple inputs. Doesn't really matter how many. It just in the real world, they cost more to manufacture, so you don't see them very often, but there's always only going to be one output. The international symbol, the square box, with this greater than or equal to 1. It's not as obvious as a multiplication. If any of the inputs is greater than or equal to 1, the output is going to be a 1. It's kind of how I remember that one. I read it that way. And the OR uses the plus symbol. So this, of course, leads to some confusion. Okay, A or B equals X is what I have written down there. Okay, something I can type in a keyboard very easily. A or B equals X to signify the OR equation, the OR Boolean logic. If either A is true or B is true, X will be true. And then the third function we're going to talk about in this slide deck, the NOT operation. Okay, it just means opposite. Do the opposite. Okay, it means there's only one possible option opposite the input. Okay, because we live in a binary world there, so it's often called an inverter or complementary. And a lot of electronics we just use an inverter. We're just inverting a signal. We're not doing logic. It's the same sort of thing. We're just going to invert the input and output the opposite of whatever came in. The symbol, the international symbol, sorry, the North American symbol, we have a triangle with a bubble on it. It's the bubble, that little round circle on the end, the bubble we call it, that is the piece that inverts. A triangle on its own will not be an inverter. We call that a buffer. We'll cover that in a few slides. But it's the bubble there that does the inversion, or creating a NOT gate. So if I have 0 in, of course I'm going to invert it. There's only one possibility. I must have a 1 output. 1 input, I'm going to have a 0 for the output. The simplest of truth tables, I could have a 0 in and a 1 out, or a 1 in and a 0 out. That's an inverter. Okay. If I had a 0 in and a 0 out, a 1 in and a 1 out, we often call that identity or a buffer. Okay, it's not making any changes at all. We often do this to control the rate that information flows. But for this, a NOT table just inverts it. It needs that bubble. We have the international symbol, and we just have a 1 in the box. Okay, just a 1 would be, a plain 1 would be a buffer. But if you look to the right-hand side of the symbol, you'll see that little triangle that's been made. That's the equivalent of the bubble. Okay, that's going to be the piece that inverts. So the 1 in the square means just do nothing. Okay, it would be just hold that information, pass that information, identity. It's the little triangle that acts as the bubble and inverts. So often people get confused by this. What does the 1 mean? Well, it means nothing. It means just hold that information and the bubble will do the inversion. When we're writing it down, more traditionally, we use a bar, an overbar system to mean the complement, okay, or the opposite, or a NOT. You won't find that bar symbol on your keyboard. So when we type this, often we just use the little hash mark after the A there, the complement of. We use that prime symbol. So the complement of A is more traditionally how we would read that. But the interpretation here, it means not A. Okay, so that's how we would write that typically on a keyboard very quickly. The NOT bar takes a little bit more work to create and build that. You will see both in the quizzes. You will see both in the exams. We want you to be familiar with both. So you will actually see those when you have to type out your answers. Of course, we don't have a overbar symbol. You're going to have to use in the prime symbol to enter in your answers. Alternate symbols. A bubble is a bubble. It really doesn't matter which ends it at. Okay, so if I have a bubble there before the triangle, I'm going to invert and then identity and then pass the information on. Or on the right with the international symbol, I have my triangle which inverts it, and then I have identity which holds the inverted value and passes it on. It doesn't really matter. I have incredibly rarely seen these symbols. I think people just do it to mess with our heads. Generally, you don't see these symbols, but technically they are just as valid as the traditional way we have these symbols with a bubble at the other end or the triangle at the other end. So what have we got here? We've got three basic gates. Okay, we've got an AND gate. If all the inputs are true, the output is true. Or you can think of it as any of the inputs are low, the output is low. We've got the OR gate. If any of the inputs are high, the output is high. If all the inputs are false, the output is going to be false. And then there's the NOT, which is just the opposite, the complement of the input, the inversion of the input. So those are the three basic gates, and we can build all our logic with those. As we're going to see later on, we don't actually do that in the electronic worlds because it actually costs us more money to make these as cheaper gates that we make, that we use. From a written and a Boolean logic, this system that we're using, these three, is usually far simpler. It's far less gates in a system, and it's a lot easier for us to handle the logic. So this is why we tend to use these three a lot when we're deciding and creating our Boolean systems. We will use a lot of these three. Going forward, for most of the rest of this course, you will be using Boolean logic. Okay, we've done some basic electronics, we've done some number system and some binary. We did the basic electronics first to get us into our labs, get us moving before we do relay logic. We did some binary and some number systems leading up towards what we're doing here for Boolean logic. So it doesn't matter if we're using pneumatics later on. It doesn't matter if we're using relay logic, PLCs, robotics. In the real world, the decisions our programming is based on Boolean, and we express it basically with these three items: ands, ors, and nots. And we make our decisions and we create our programs. We build our factories, we build our cars with these three basic concepts. Okay, so they're the foundation of really most of what we use in our society today. It was built by a machine, it was built by a process. Even if I was to take something like a baseball bat. Now, baseball bat, that's a very analog thing to make. We look at the timber, we look at the grain of the timber, okay? But already we're making decisions, okay? Is it the right wood? Is it the right dryness? Is the grain correct? Is the orientation correct? We're doing ands and ors and nots in that analog process to make something like a baseball bat, okay? So even in non-automated processes, we use these subconsciously to make our decisions, ands, ors, and nots. The symbols we're going to use, I just remember that this one that looks kind of like a D must go to the and or not. There's only one D in those three words, so that tells me it's an and. The or must be that other symbol, that kind of like an arrowhead type symbol. A not, well, not is an inversion, so it would have one input and one output. That must be the not. So that's how I just remember the symbols, and you'll find fairly quickly that these are fairly simple to memorize and use. You don't have to use them a lot, and you're starting to recognize and use them very easily. How I would write it down, I've got here the first one, A and B, A with a dot and a B. Now usually it's not a big heavy dot like that. It's usually just a simple period type dot. I've got a big dot there just for teaching purposes. A and B equals Y, or AB equals Y. I can write it out, A and B equals Y, more explicitly what this means. A plus B equals Y. Well, it's not plus, okay? It's A or B equals Y. Okay? Most people are going to see that. Oh, that goes back to mathematics in high school when they started using letters instead of putting numbers in there, and I complained that this wasn't really math. That's not the case. This is just Boolean logic. A or B equals Y. And then the nots, the overbar symbol, which we typically use when we're writing it by hand. It's very quick, it's very simple. Or the prime symbol, which is available on our keyboards to indicate not A, or also often said A not. People will say it one way or the other. It does get a little confusing, as we'll see as we move on. So exercises, I'm just going to switch to my whiteboard. Exercise 1, Jacob, see you're online. What would the answer to be, the first one be, the top one on the top left? Jacob? 0? Correct. Okay, we've got Emmanuel. What would the answer to the one beside that be, please? Emmanuel? Either say it or type it in. 1? Nope, it's an and. Okay, so you've got 1 and 0, or you can think of it as 1 times 0. That would equal a 0. Okay. Pierre, the next one, please. This one over here on the left. A 0, correct. 1 or, sorry, incorrect. 1 or 0. Okay, so remember the European symbol that we use, greater than or equal to 1. Okay. If there's anything greater than or equal to 1, yes. Okay. If I add them up together, it'll be greater than or equal to 1. 1 or 0 is going to give me a 1. We've got next, Ty. Ty, this last one, please.
Would that be a 1?
Correct. 1 and 1 equals 1. If all the inputs are true, the output must be true. Good. Thank you. So I've just said this here. If all the inputs of an OR gate are low, the output is going to be low. Okay. If any of the input of an AND gate is low, the output is going to be low. The output of an OT gate is always the opposite of that input. Completing the truth tables, okay? Now we're starting to get a little more difficult. Typically, the way I use a truth table is I create a truth table and then create the logic, okay? But in this case here, we're trying to teach what a truth table is and what the outputs would be. So we're going to create a truth table for the appropriate symbol. So Steve, could you tell me what the 4 items for this symbol here, this first symbol, are? What would the outputs be?
For the first one, is it 0, 0, 0, and then the last one is 1?
0, 0, 0, 1? Nope. This is an OR.
Okay.
Okay. So what would it be?
The first one would be 0 then, wouldn't it? And then the second one would be 1, and then 1, and then 1 again.
Correct. Yep. Exactly. If any of the items giving a total here of greater than or equal to 1, the output is going to be 1. It's kind of how I remember what that is. Okay, if I was to add these up, these inputs, and I'd get a sum of greater than or equal to 1, the output therefore must be true or 1. Okay. Tanner. Is Tanner there? Yep.
Yep.
Next one, the AND symbol. Well, I gave that away. I told you what it was. What are the outputs, mate?
0, 0, 0, 1.
Correct. Okay, it's an AND gate. Okay, now just a little bit harder to do. Okay, say I've got 2 switches. These are switches just like you have to turn on the lights in your room, in your house. Okay, 2 plain old switches. They're not connected to anything. But I want to create an AND. I don't recommend doing this. This confuses the hell out of the inspector from the city. I've done this in my house. It has odd, quirky lighting that the inspectors always got confused about, and they grudgingly accepted it. But if I wanted to create an AND, I've got two switches, and I want to create an AND. Okay, so A and B must be true in order for Z to happen. How do you think I'd connect those together? Anyone? Open it up to everyone.
In a series?
In series, exactly. This would be the AND, the A, this switch would be the B, and if I connect them up in series, I've got my output. If A is closed and B is closed, then Z is acceptable. Z is true, okay? So yeah, just wiring them up in series will achieve that. So now I want to create an OR gate. So I've got C and D and Y. Okay, so I want these same two switches, but now I want to wire them up so that if C is true or D is true, the output Y is true. Okay, so I've got an output Y. How would I configure these up? How would I wire them up?
Do you have one on each side? So if one is powered, then instead of having in a series, have them.
I've got one word I'm waiting for, just one more
Would you make
word.
them parallel?
Parallel, yeah, that's the word I'm
Yeah.
waiting for. Okay, so if I have them in parallel, okay, if C closes or D closes, okay, then the output is true. I rewired my wife's cousin's house, and they had 3 horrible sets of switches that had been configured in this way. So someone had thought they'd want, the lights on the stairs to be powered from either the top of the stairs or the bottom of the stairs, but they'd done it this way. So if you wanted to have to turn the lights off, you had to shut them both off. So you might shut off the lights downstairs and then go upstairs, shut off the lights. Well, now the lights turn off and you got to climb down the stairs in the dark. Not a great way of doing it. Okay, but this is how we can, with basic switches, start creating this sort of logic. Okay, we don't need a fancy gate. We can just do it with our existing switches, create these kinds of decisions. So moving on to exercise 5, a little bit of automation at a tank farm. I'm moving chemicals from one place to the other. Now, the problem solving. Problem solving, the first and most important thing is to read the question. Read it, make sure you understand it before you even try to start solving it. Otherwise, you solve the wrong problem. So step 1 in Chris's basic problem solving technique, read the question, understand the question. So if I get something from a client and they say, Chris, we want you to do this automation for you. Here's all the requirements. I read the requirements. And then I go back and ask them, this doesn't make sense. What do you really want here? Or, well, you've left this without a decision. Is this important? Or, hey, PS3 is not even used. What does PS3 get in there for? That's just throwing money away. Did you miss something? I analyzed the requirements. I sat down and read the requirements for a tank farm in Fort McMurray. And I read about 2 pages, and I went to Andy, the guy who asked me to read this. I says, this is garbage. I says, there's not enough information here. There is nowhere enough of information. I didn't need to read the whole 200-page document. I was at 2 or 3 pages, and I could easily see there was massive amounts of missing information. So the first thing is to read it. Okay, so if I read this, what have we got? There's a pump. It's used to move liquid from tank A to tank B. Okay, that sounds simple enough. If PS1, PS in this case is pressure switch, okay, PS1 and PST are closed or true, okay, the pump can operate if PS3 is not closed, false. The wording of that is awful. Okay, you got to twist it around and you think, oh, what the heck are they really asking for? Take notes even. Okay, you start writing down a truth table to solve this. And often the wording from a client is a little backwards like this. That's why I've deliberately created it this way. I've drawn a small diagram there. showing tank A and tank B. I've got 3 pressure switches and a pump. I've got fluid flow from A to B. Then I've got first question. What is the Boolean equation to control the pump? Okay. So what would it be? I'm going to go through this slowly and talk about my logic of how I got or get to an answer. If I start looking, the first sentence, if PS1 and PS2 are closed, there's an and here. Okay, and. So I've got PS1 and PS2. The pump can operate. That's my output. It will be true if PS3 is not closed. It doesn't say and or if. Sorry, and or. But I'm going to look at that and go, oh, that's definitely an and, because I've got these first two, and this PS3 has to be not closed. Equals pump. This is my Boolean equation. I look at my inputs. I've got 3 of those inputs. They're all going to be used to control my single output, which is the pump. PS1 has to be true. Yep. PS2 has to be true. Yes. PS3 has to be false. Yes, in order for the pump to turn on. There's my simple little Boolean equation in order to make this work. Then it says create a truth table for that Boolean equation. So I'm going to show you how I create the truth table. Okay, a little quick way of solving that, creating that truth table. Just scroll down and give myself some room here. So if I notice, I've got 3 inputs. I've got 3 inputs. I've got PS1, I've got PS2, PS3. There's my inputs on the left. I've got 1 output. It's the pump. Okay. I've got 3 inputs. Now remember, I said if I've got 3 inputs, that is 2 to the 3 combinations of inputs. I've got 3 inputs, so if I combine every which way possible, I am going to have 2 to 3, which equals 8 inputs. So how do I start writing these down? I don't want to miss any. Okay, so I have a simple technique. The first half of this 8, i.e. 4, are going to be zeros for PS1. The second half are going to be 1s. PS2, the first quarter of PS2s are going to be 0, then 1s, 0, 0, 1, 1. See the pattern? Of course, PS3, I'm going to write 0, 1, 0, 1, 0, 1, 0, 1. Now, some of you may recognize, oh, this is binary. This is binary for 0, 1, 2, 3, 4, 5, 6, 7. And you're absolutely right. Okay? It's a very simple way of creating this truth table. Every possible combination of inputs for my 3 inputs is now created. Okay, and now the part is the pump's output. What are the outputs going to be? Well, if we look back to my Boolean equation that I have there at the top, PS1 has to be true. For the pump to turn on, PS1 has to be true. PS2 has to be true, and PS3 has to be false. So if I look at my PS1s, wherever there's a 0, the pump must be off. Because remember, every input must be true. So if a single input is false, the pump will be off. So PS1, wherever it's a 0, the pump is going to be off. PS2, wherever that is a 0, the pump is going to be off. PS3, oh, this is different, it's a not. Whenever PS3 is a 0, not, i.e. the pump will be off. So when the PS3 is a 0, the pump will actually be on, okay, because we're inverting it. So the PS3 is a 0 here, These other ones are not going to be on because, of course, PS1 and PS2 are zeros. So I'm going to have PS1 on, PS2 on, and PS3 off to give me a pump out. And with PS3 is therefore a high, inverted to give a zero, I'm going to have a pump being off. And there I have my truth table. Okay. So I quickly created a truth table for this equation. I can see from this truth table, logically, that I'm only going to have one situation where the pump is going to be on, where these have to match. And if I look closely, this matches my equation. PS1 is a 1. PS2 is a 1. PS3 is a 0, and the pump will turn on. Okay, this matches my equation. So the third part of this is draw the Boolean gate logic. What have we got here? If I think about my equation back up here, I've got an AND. I've got another AND. And I've got a NOT. Okay. So I'm going to use AND gates and NOT gates. We've got an AND. One output, two inputs. PS1, PS2. PS3 needs to get inverted. Okay, so that's that AND taken care of. That's that NOT taken care of. I've still got this AND to do. So I'm going to AND together PS1 and PS2. I'm going to AND it with a NOT PS3. So I'm going to need another AND symbol. I'm going to take...
Hi, Chris, can you hear me?
Yes, I can hear someone.
What about, I mean, this could be used in the real world as well with saving money and resources. What about only having one AND gate and one NOT gate? Having an AND gate with 3 inputs, putting the NOT gate before the AND gate for PS3, and then that goes into one input of AND, and then PS1, PS2 go to the other 2 inputs, and then you have your gates. Yeah.
It's actually very expensive to manufacture that chip, that part. Yeah. It's very difficult to manufacture. The usage case for it, of course, would be very, very low. How often do you want this? So from a scale of manufacturing, it's a no. The actual manufacturing process where we take a silicone and we deliberately impurify it in a certain way. We make it perform a certain way. These gates are very expensive compared to others. Okay, so this gate here that I just created would be horrendously expensive to manufacture.
Oh, okay.
And to dope a piece of silicone to do that is actually more expensive than taking my silicone and doping them to make these operations.
Mm-hmm.
So from an environmental perspective and a cost perspective, we don't do that. Yeah.
Okay.
Okay. So that was a worked example, example 5, a kind of a real thing we're going to do in a factory, how to interpret it, how to create a Boolean logic. We'd create a truth table, okay? I just keep going back to truth tables time and time again in the real world in order to better communicate or better isolate the performance requirements. And then I've got a simple little logic here, okay? We're going to see how we could actually do that with relays. We're going to see how we could actually do this with a PLC instead. And then, of course, with a PLC, it's just a piece of programming. That's zero environmental impact, minimal cost, way better control. Okay. So let's have a look at exercise 6. I'll get you guys to do this on your own. Otherwise, I'm going to run out of time today. Usually in an in-person class, I've actually got a small robot that I show this operating a small self-guided robot to demonstrate this, but I'll leave exercise 6 for you guys to do on your own. Exercise 7 we can quickly do. Does anyone have an answer for me on this first one? The two binary states can be identified as either A, high and low, B, on or off, C, 1 or 0, D, all of the above.
Would it
Anyone?
be D?
All of the
All of the above, yeah. Anything. Red and blue. Okay. The Oilers and the Canucks. Okay. Any two distinct things, okay, can be used for binary states. A gate can have one or more outputs, but only one input. True or false?
false.
False, correct. It can only ever have one output. It's the whole point of making a decision. I need a decision with a single output, regardless of the number of inputs. Okay, so the US is going to have an election. Wouldn't matter how many people are running for president, only one of them is going to win. Okay. Now I've got here a sentence with a missing word. The missing word could be input status, data, output status, or truth. The missing word table shows the resulting output for each possible gate input condition.
Truth.
Truth,
Truth.
yeah, truth table. A light that is off or a switch that is open would normally be represented by a binary 1.
False.
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 Yeah, false.
Okay, now the important thing here is to notice normally. Okay, some systems we do reuse a reverse logic. Okay, we inverted logic for the entire system. I typically don't like to do that. Sometimes there's electronic reasons to do it. I don't like doing it because most people struggle with it and make mistakes along that process. So I have this word normally in there because it's not exclusive. We will sometimes have systems where that's the opposite. The OR function, implemented using contacts, requires contacts connected in series. True or false?
False.
That'd be false. They should be in parallel.
In
Yeah,
parallel, correct.
parallel.
You see the word there I've used contacts. In this case, the example we did before was switch contacts. You're going to see in your labs we can use relay contacts. Contacts is kind of a generic term there, meaning two connectors, two things connected to conductors that we open and close. Excellent. So 8:53, perfect timing. Let's take a quick 7-minute break because that'll round us out to 9 o'clock. And I'll start on presentation 1.5. And presentation 1.5 is just applications of these 3 gates. Okay, we're not really going to talk a lot of new material, but we're going to use different tools in applying or looking at these gates, because there's more than just writing down Boolean logic or using equations to analyze the performance of a Boolean logic. So I'm going to look at some of those tools and apply them for the next slide deck. Any questions? Basic digital control applications of and, or, and not. Once again, variations on this can be found in the textbook. So slide deck 1.5. Let me just get rid of those meeting controls. In case there was something at the bottom of the slide we want to use. First thing I want to talk about is timing diagrams. We can analyze a circuit, we create a circuit, but the things we're creating, even though they're digital circuits, they're still made by real world items. To look at a pure Boolean circuit, it's still a silicone-based circuit. It still has microwelds. It still has potential defects. It still has soldering in it. It's a real world item, and no two things will perform exactly the same. So sometimes you run into issues where a circuit does not perform as expected, and we use timing diagrams. I'll often connect things up to an oscilloscope to analyze and to see what's going on. So timing diagrams are a very important tool to analyze or predict what will happen in a circuit, or do troubleshooting. When you buy a chip, a microprocessor that you're thinking of using in a board, the data includes numbers after numbers of timing diagrams in certain conditions, so that the person selecting it has a good idea of what the lag would be, or the delay would be, or how long the input conditions must be held before the output can be trusted, things like that. So a timing diagram is a common tool that we use in electronics. So I'm going to cover timing diagrams. So here I've got an example of a basic timing diagram for an AND gate. Now this is perfect, ideal, unrealistic in the real world. We don't usually get these nice square waves. We usually have some sort of overshoot, some rounded corners. They may not be perfectly vertical. The logic 0 and the logic 1 may not be perfectly flat, but you can get the idea of where we're going for this. So if I look at A here, A is an input. A is an input that changes from 0 to 1 and back again with time. So not drawn on this, on the right, on the axis at the bottom, that would be time. As time goes on, logic A and logic B are changing. As a result of those changes, the output is going to be changing. So if I look on this first one on the left there, we've got A and B. A and B are both at logic 0. A and B, 0 and 0. The output is going to be 0. The first change, I've got this little dotted vertical line there. I often draw these in to help where a change occurs, an input changed. There's a possibility of the output changing if an input changes. So the only place an output should change is if an input changes. The input change here is A goes to a logic 1. So just after that first dotted line, you can see I've got A as being a logic 1, B is a logic 0. This is an AND gate we're analyzing. So the output would be a 0. 1 and 0 should produce 0. So you can see the next change, B is now a 1. A is 1, B is 1. So therefore the output Z would now be a 1. And you can analyze that from left to right and see that this is how a timing diagram is used. Okay, I can analyze it. I can look at the Z instead of having a truth table or something like that. This is one method of analyzing the performance of a circuit or a gate. Okay, so I can use a timing diagram in my application of this little piece of Boolean logic. I can do the same with an OR. In this example here, I've gone one step further. I talk about baby steps. Those will get me in second year. Will be tired of hearing this term. Those of you, I've had students up to 5 different courses over 2 years, tired of hearing this term, but I keep going back to it. If you're having trouble, go back to the smaller steps, the baby steps, the increments. Here I've added a baby step of actually writing in logic 0 and logic 1 after each transition. So I can read it downwards, 0 or 0 equals 0. I can see 1 or 0. The answer there I haven't written down, that would be 1. The next one, 1 or 1 would be a 1. 0 or 1 would be a 1. 0 or 0 would be a 0. Okay, so I've just written these in to help clarify and do my Boolean logic. Okay, once again, it's just a timing diagram where the inputs vary over time and the output as a result will vary over time. Time moving from one way to the other, from the left to the right in this example. Okay, so I'm going to do this first one and then I'm going to ask people to start helping me afterwards for the next one. This first one, it's A and B equals Z. I've already written in the possible changes for A as it progresses over time, and I've got the input B, I've got an output Z. As time progresses, I have written in or drawn in already vertical lines where input transitions occur. Okay, so I've got a 0, 0. I know 0 and 0 gives me a 0 up to this transition line. We have a 1 and a 0. Boolean logic, 1 and 0 gives me a 0 through to the next transition line. A is now still a 1. B is now a 1. 1 and 1. Give me a 1. Through to the next transition line, etc., etc. So I can keep drawing my output. Successive transition lines, to create my output for my timing diagram. And now it's complete. Okay, broke it down into small steps and created a timing diagram. So exercise 2. William, I see you're online. Let's get you to help me with this timing diagram. I'm going to put my pen down here. I'm going to start it here to the first transition. So William, after this first transition, should I be a high or a low? Are you there, William? Did he just log off? And nope, I've still got him here. No mic, William, if you're trying to talk. Hello, William. Can you hear me? Can anyone hear me? I've been talking to myself for the last 10 minutes.
We can hear you. We can hear you.
Yeah.
Sorry, my computer's being really slow.
William, okay. So I'm up to this first transition line. Will I be high or low after this transition line?
Well, I'm going to say low.
Low. So this is an OR. After this first transition line, A will be a 1, B is a 0. 1 or 0 should be a
1.
1. So they're going to be a 1. What's next after the next transition line? Is it going to be 0 or 1?
I don't totally understand what you're asking.
This next line that I'm going to draw either here or here. Is it going to be a 1 or a 0? Because I've got two inputs. I've got input A and I've got input B. Over time, those inputs change. Therefore, the output Z will change. Okay, so we have up to this point here, this transition line, established an output. This transition line is drawn if an input changes. As we can see, B changed. B changed to a 1. A is still a 1. So what would the output Z be for an OR gate?
A 1.
A 1, correct. Through to the next transition line. What would the output be after this next transition line?
0.
A 0. No, this is an OR gate. I have a 0 or a 1.
Oh, okay. Well, that would be 1.
A 1. Next line. 0 or 1.
1.
I've got a 0 or a 0.
Oh, okay. Well, then that would be 0.
Next one.
So it's going back up then. It'd be a 1.
Correct. Next one.
That'd be a 0.
Why is that?
Well, because would it not go back down there?
I've got input A, that's a 1.
Okay, it'd be
Input
1.
B is a 1. So my output will stay high. Next one.
That one would be a 1 as well.
Correct, that's a 1. Next one.
That one would be a 0.
Correct, yep. And there we have my timing diagram drawn using an OR gate, okay? So we can see and we can predict, we can create the output for a series of inputs or a pattern of inputs or whatever the real world is of inputs. We can create an expected output. And the idea of building this timing diagram is to understand how they work so we can use them in our analysis of a circuit. So here's an application of an AND gate. An AND gate is often used as what's called a steering gate. We can either pass a signal or stop a signal from going past. Okay, we can enable a signal to be transmitted, or we can shut it off, much like a switch. If you think about it, if I connect a switch up to one of the inputs, okay, say control 1, if control 1 is low, it doesn't matter what the signal coming into the other input, the output is going to be low. If control 1 is high, the signal coming into the gate is just passed through the gate, because whenever the signal is high, I've got a high and a control 1 being high, the output's going to be high. If signal is low and control 1 is low, the output is low. Think of you remotely turning on your Bluetooth speaker. Okay, your Bluetooth speaker can get signals all the time. Okay, I turn it on and it can output my signal. Okay, so I can use it as a control gate. Anything coming from a signal can get passed through if the control is at a 1. Okay, if the control is at a 0, nothing goes through. Everything gets blocked because it has to be ANDed with a 0. Anything ANDed as 0 is going to be a 0. So sometimes an application of these is just to turn things on and off electronically. Now we're moving into combinational logic. You would have heard me speak. You've seen a couple of visual examples of this logic. And as we've seen, until you start combining it, you're not really making much of a decision. So combinational logic describes digital logic circuits that are based on an array, a number of logic gates. Now, combinational logic doesn't remember anything, okay? It just forgets everything. It's got no memory. If you lose power, it's lost memory. Okay, now combinational logic, we can talk about this in English terms. Okay, so you've heard me use ands, ors, okay, those verbal kind of words. The Boolean equations, we saw examples of that, where I had A dot B. Truth tables, we did that. We started with truth tables. That's generally what I start with when I start with designing a logic result. Logic diagrams, okay, that's using those little symbols that we have, the and symbol, the or symbol, and the not symbol, and then timing diagrams that we've just covered. Okay, different ways of describing what is going on or what our intent is. So here's an example of a circuit, nice simple circuit. I've got 3 inputs, 1 output. I've got 2 pieces of logic. Okay, and I've written this as a schematic. So what's going on here? Just hide that. Wait a second for that to disappear. Okay. So I can see this and I can describe it in English terms. A and B. Okay. ORed with C equals Y. Now, just verbalizing it can get a little confusing or very confusing. Okay, so English terms are not the best, okay, method of describing this sort of logic once it starts getting complicated. We want to use a diagram or an equation. But here it was. We've got A and B or C. The comma there indicates a pause. And the way I say it would be with a pause. A and B or C equals the output of Y. So I can maybe listen carefully, or get you to listen carefully and understand what I mean, but it's certainly not going to be as clear as this diagram is. We have A and B that point after the AND symbol, and then that is an input to the OR gate along with an input C, and the output of that OR gate is Y. Far cleaner, far simpler to write an equation down to verbalize it in English terms. If I want to write that equation down without using a schematic, I can write down A and B or C equals Y. A and B, they have parentheses around them. If you didn't write it that way, someone might think that the B and C are ORed together first and then added with the A. So to clarify, I'm going to use brackets around A and B. That is a gate. A and B is a gate, and it's ORed with the result of A and B is ORed with C to create my output Y. I can use it to create a truth table. Okay, so I've got my little diagram here. I've got the equation that I've written down for clarity. And next, we're going to create a truth table. I have A, B, and C, 3 inputs. 2 to the power of 3 means 8 possible combinations of inputs using 3 inputs. And that's what's on the left-hand side of that truth table. On the right-hand side is the outputs. If I analyze that, if I analyze the gate logic there, well, I've got a C going right towards the end and being ORed with something else to create Y. If any input on a OR gate is true, the output is true. So I can say, hey, look, I can shortcut. Everywhere the C is a 1, the output is going to be a 1, right in the ones. My other gate, A and B. Whenever A and B are both 1, the output Y is going to be 1. And then I fill in everything else in the Y column with zeros. Okay, so you will see I have 3 zeros and 5 1s to create this truth table. Okay, truth table describing A and B or C equals Y. Okay, or the pictorial that we have there, or the written Boolean logic, all describing the same thing as this truth table. I can even create a timing diagram. So I have here 3 inputs changing over time. This is more typically what I do with a timing diagram if I'm trying to communicate how it works. If I look carefully at this timing diagram, A, B, C, it matches my truth table. As we move through time, left to right, A is all 0, and then it changes to 1. Just like my truth table, working from the top to the bottom, all zeros, then all 1s. You can see B changes from 0 to 1 while A is 0, and then from 0 to 1 again while A is 1, just like in my truth table. And the period for C is half as long as it was for A. Okay, so it's cycling 0, 1, 0, 1, 0, 1, 0, 1, just like my truth table. And then I've created an output Y. Okay, and it corresponds to the column Y in the truth table. These are all methods of describing exactly the same thing. And we need to be familiar with all of them and move backwards and forwards with them and to be able to interpret them. So I've got one here, and it looks very much like what we had earlier. Someone asked about creating an equation that looked like this. Yes, it can be done. I've got a combinational logic of A naught and B and C equals Y, or not A and B and C equals Y. And then it's drawn there as a schematic, as a piece of gate logic describing the output. Once again, I can create a truth table. If you look at my truth table, I've added a baby step. I've got an input A. My input A is inverted, so I've written a column with A inverted. I've got B and C. And then if I look at A naught and B and C, okay, and I will create column Y. So in column Y, if A naught and B and C are all 1, the output Y would be 1. Otherwise, the output Y will be 0. So I can see that A is a 0, B is a 1, and C is a 1. That's the only time the output Y is a 1. I've got a timing diagram. The ABC on the timing diagram is drawn exactly like it was in the previous slide. But if you look at the output, you can see the only time the output is high is when A is a 0, B is a 1, and C is a 1. These are all describing exactly the same thing. Okay? Different tools that we can use to analyze a piece of logic. So how do we do this? Okay, I might start with a circuit diagram like we did in the previous 2 examples. I want to create the Boolean. How do I go about doing this? It's a step-by-step process. It's a logical, sequential series of steps in order to create this equation from a circuit diagram. I've walked into a factory. There's a piece of logic. What does it do? What are the inputs it's doing? What is the control mechanism? So real world example, I have a client who wants to automate something with a PLC. Here's the existing piece of equipment. That's all we have. We've got no paperwork. We don't know what it does. We don't know what the intent was. If I analyze the circuit, the performance of the circuit, I can create a Boolean equation. From that Boolean equation, I can create my code for my PLC. Okay, and have something moved to a PLC. So how do we do this? We begin at all the inputs. We want to know what all the inputs are, how they change. We want to include all the logic expressions. And we move our way from the inputs, the knowns, towards the output. We move through all the unknowns in our process as we start to build this. So if I have something like this, I've got a logic on analyzing this logic circuit. Step one, working from the left, I've got A and B. Okay, and I keep analyzing the output of that, and I find it goes to an inverter. So I've got not A and B. I keep analyzing that, and I can see that it goes to an OR gate. Oh, what's the other input for that OR gate? I analyze my circuit, and I see, oh, it just comes from C. So I'm ORing C with the knotted AB. I have built my equation, y equals not AB or C. Step one, Vincent. You available, Vincent? Yes, Vincent. Okay, so step one. What would be the expression here for step one? A or B, correct. Okay, A or B. And then we're going to AND it with C. So we'd have A or B, and we're going to AND it with C to get Y. Okay. Exercise 2. Tyler. Yeah, Tyler, not Ty.
Yeah.
Can you, yep, okay. So step one, what would step one be here? Exercise 2.
Step one?
Yes.
It would be an AND, so it would be 0 or 1 for it.
I want to convert this to the Boolean expression. I don't know what the values of the inputs are.
Oh, it would be A times B or A and B.
A and B, correct. So what would step 2 be?
Step 2, that would be, it would be the invert of A or B.
Yep. Step 3.
That'd be the invert of B.
Correct. Step 4.
Or that would it would be A it'd be A or B put together from everything else.
A or B put together from everything else.
That sounds bad.
Yeah.
It would be A or B. Yeah.
That's what you just said to me.
Yes.
So I want to OR together. Step 3
Oh, wait.
and step 2.
Okay, so it's A or B or B again.
Oh.
No.
It's A. Step 2, A and B knotted, ORed with B not. Okay? It's AB knotted, ORed with B, and that will give me my W. Okay? Good. Next one. Rohan. You there, Rohan? Hi. Can you answer this one, exercise 3, please, mate? What would step 1 be? AB, correct. Okay, step 1 is simply A and B, or AB. What would step 2 be, mate? Yes. No. Quite. Not quite. You've got A or B. It'll be C. Remember, it's C and D. C or D. Okay. Step 3. Careful on the typing on this one. Rohan? Not sure, to be honest. Okay. So what we're going to do is we're going to OR step 1 and step 2. So I could just go AB. I'm going to put brackets around. Okay, that was a single gate. That runs into this OR statement. The other input to this OR statement is my C or D. Okay. Z. We could just leave it like that. Okay. I'm not asking you to simplify it at this stage. Okay. Just leaving it like that would be a perfectly acceptable answer. Okay. So next one. Exercise 4. Seth. Can I get you to do this one, please, Seth?
All right. The first one would be A or B.
Yeah, so I've got this big equation. I haven't written any steps or any here, but I can simply say, okay, I know this one here, that's A or B, baby steps.
And then it would be C and D.
Yeah, that one there. C, D, yep.
And then the upper one would be A or B and C and D. And then the lower one would be C and D or D. And then the last one would be A or B times CD and CD plus D.
Perfect. Okay. Just break it down into the little baby steps. It's an iterative process. Okay, and at the end you've got something that's kind of complicated, but you didn't really have to think about it. Just a whole lot of small thoughts, sticks it all together. Okay, excellent. Well done there. Oh, that's the last exercise in that one.
Isn't it CD plus D, not CD plus C?
Sorry, plus, yes, my mistake. Me rushing ahead and not listening. I even have it written correctly above it. Yes. Okay, now we want to work back the other way. Okay, I want to be able to do a Boolean to a circuit. I've been given a piece of Boolean and I want to create a schematic for it. Okay, I want to create a piece of code with it. I could do anything with it. In this case here, we've been tasked with creating a small schematic. Once again, it's a step-by-step approach. It's a small one, but we want to work outwards. We want to convert A, B, C in this case, A, B naught, C, ORed with BC knotted to create Y. What we do here is we work backwards. We work from the output back towards the input. So if I look at that, my output is a Y. I'd write down the Y. I know an output is a single output of a gate. If I look at my equation, I can easily break it into two around the OR. So I draw an OR gate, which has two inputs. One input is A, B, not C, and the other input is B, C, all knotted. Okay, so step one, starting from the outputs, working our way towards the simplified inputs. Step two is I have a look at each of those inputs and see what I can do with those to start creating my equation. On one side, I've got this A, B, not C. I can say, hey, that's a great big AND gate with three inputs, A, B naught, and C. Well, A and C are good. They're raw data, but B naught, that's been inverted. So I need to take that input from the B naught and invert it so I get back to a nice clean B. So I've got A, B, C there as inputs. The other side of my OR gate, it's a BC all knotted, so there's an inverter in there. So if I get rid of that bar for the inverter, by putting a NOT gate in, I've got a simple B and C. Two input AND gate, B and C. So step one, break it at the OR gate. Step two, take one of those inputs, break it down, do an AND gate, an inverter. Step three, take the other side of the input from that OR gate, invert it, break it down to a B and a C, and it together. Step four, I put it all together. Okay, so I've got this equation and a circuit. It looks kind of ugly, so I want to neaten it up, I want to tidy it up. I've drawn it in the more traditional manner, from left to right. But you'll see there I've got B mentioned twice and I've got C mentioned twice. I don't really like that. That may lead to some confusion. Why is there two B's? Why is there two C's? That doesn't make sense. So we'll just tie them together and we create a circuit that looks kind of something like that. So the simple method of doing this is to start from the output. Baby steps. An output, well, that's a single output. What sort of gate is it output from? And start breaking the equation down in those logical places. It's an OR gate. It's got two inputs, etc., etc. I just work through those series of small steps and I can create a schematic from the equation. Okay. So looking at the exercises here. Exercise 1, I don't believe I have this on my whiteboard. Draw the circuit whose expression is ABCD. What I'm going to do is I'm just going to create a blank space in my whiteboard and share that.
It was AB plus CD equals X.
Nice and simple. Excellent. So the first thing I do, I'm going to look at my output. There's an X. It's an output. What sort of gate is it going to be out? Well, obvious breakpoint is an OR. So I'm going to draw an OR gate. I can see it's got two inputs to my OR gate. Excuse my incredibly bad drawing. Let's take first input. It's an AB. It's an AND gate. With two inputs, A and B. My second one, it's an AND gate. Two inputs, C and D. And we're done. Simple as that. Okay. Starting from the outputs, working towards the left. Can you tell me the next one, please?
It was AB plus not BC equals X.
Is that correct?
Yes.
Good. Okay. So same thing. I've got an output. X. It's going to be output from a gate. The gate is going to be, there's a logical break.
OR
It's an OR gate. The OR gate has two inputs. One of those inputs, we'll start with this one, is simply an AND, two inputs, A and B. The other one, that's got a NOT symbol, an inversion. So I've got rid of that NOT. I've got a B and a C. It's an AND. The B, can tie up to the other B, and we have our answer. Okay. So once again, it's a systematic system of small steps. Break it down into small steps and just solve it in a sequential, in a logical manner. Okay. And we can see they're starting to get more and more complicated. Okay, I've got a not in this one. Exercise 3, I've got a not over everything. So the first thing I'm going to do to my output, I'm going to have the inversion. I'm going to get rid of that. The input to that is I can see there's an AND. Okay, so I'm going to have an AND gate. I'm going to see there's two inputs, A or B, or not AC. And just keep working backwards to the left, breaking it down, creating my schematic. Okay, so it's just a sequence of steps. I'm going to leave this motor control. Well, no, we're going to go through this motor control problem. Let me just get rid of the toolbar. So, motor process control program. A mixer motor is to be used automatically to stir the liquid in a vat when the temperature and pressure reach preset values. So if I read this and I start thinking and taking notes, I've got an output here, it's a motor. I can see that I've got two inputs, a pressure and a temperature. And a little bit of logic is when they reach a preset level, the motor will turn on. Okay, that makes good sense. The second statement, manual operation of the motor is provided by a means of a separate push button. So I could also operate by pressing a push button. That's another input. Okay, the implication here is, oh, that's an OR. Either statement 1 or statement 2 can make that motor run. And then the question is, what is the Boolean logic to implement those requirements? So having read those requirements, I should be able to create the Boolean, design the circuit, create the truth table, create the timing diagram. Should be able to do all of those things from this simple word problem. First thing, always, Chris, read the problem. What I like to do is identify the inputs. I identify the outputs. My preference, create a truth table first. It's what I usually go to 99% of the time. I create a truth table. The beauty of the truth table is that if I have any X's, any unknowns, okay, oh, I've got an output here or a set of input conditions where there is no output specified. I can go back to my client, to my customer, and say, what do you want to do in this situation? I shouldn't guess. You know, if they say, oh, we'll just leave it up to you, then okay, that's on them. I've got that in writing. But if I've got some unknowns, I want to do that. So this is why I want to identify those inputs and those outputs, create the truth table. If I've got any unknowns in my truth table, I can go back and update the information. So what did we say? It's basically two control operations. A mixer is to be used to automatically stir the liquid in the vat when the temperature and pressure reach preset values, i.e. if the temperature is true and the pressure is true, the motor should be true, on. Second one, manual operation of the motor is provided by means of a separate push button. If the push button is true, motor should be true. Okay, these are my requirements that I've interpreted by reading it. I have my inputs. I'm going to assign them letters because I don't like writing in temperature switch and pressure switch and push button switch every time. In this case, I've just simply assigned the temperature switch is going to be a T, pressure switch in my schematics a P, and the push button switch will be B for button. My outputs. Oh, I've got a mixer motor. There's only one of them. I'm going to give that an M. Then I start building my truth table. I've actually divided the truth table into two parts here to fit on the screen. But you can see my truth table, it's got 3 inputs. 2 to the power of 3 is 8, so I've got 8 possible combinations. And then I've created my truth table. The left-hand half was all the T's are zeros, and then the PBs are the various combinations. And the right-hand one, all the T's are 1, and the PBs are the various possible combinations. And you can see in blue, whenever the push button is a 1, the B is a 1, the motor needs to be on. Okay, so I've written 1 in the motor column. Whenever the temperature and the pressure presets are reached, i.e. that both have to be 1, the motor will be on. Every other case, motors are off, zeros. Okay, so I've developed my truth table of when the motor should be on. I've got these 5 conditions. Based on all the inputs, there's 5 conditions when the motor can be on. Okay, now I can write that Boolean expression a lot simpler. I can see T and P have to be on, or B has to be on for the motor to be on. Okay. I can quickly verify that from my truth table. Now, it may have been obvious from the first 2 statements, this was my Boolean equation. My truth table proves it. Okay, I keep going back to my truth table because it contains a huge amount of information, not what's just true, but what is false and potentially what is unknown. So that's given me my Boolean expression and my truth table for this problem. And that is the end of that slide deck. Let's take a 5-minute break and we'll come back to the next slide deck, which is 1.6, and we'll move through that. We'll get through 1.6 easy today. 1.7 we may not finish today, but 1.6 we should be able to get through today. Any questions?
Nope.
This next slide deck, is about NAND and NOR gates. And they're introduced as the universal gates. And universal because I can actually make every logic decision just through a series of NAND gates, or just through a series of NOR gates. That's why they're called universal. In fact, most of our electronics are NAND gates. NAND gates, they're incredibly easy to make. You can make them really, really small. They are fast compared to the other gates, and they're dirt cheap. So all the fancy electronics going on your computer, in your phone, your iPad, whatever it happens to be, it is primarily driven by billions upon billions of NAND gates. Okay, so that's why they're called a universal gate. They can do it all for us, and it tends to be what we actually use in our process. So from a combinational logic, previously we talked about an AND gate and a NOT gate. If I combine them together, I'm going to get a NAND gate. Okay, instead of having 2 separate gates, I dope the silicon appropriately, and I get a single NAND gate. The NOT gate is attached. Put a bubble, just a bubble from my NOT, put it onto the end of my AND, and now I have a NAND. Here's my standard North American symbol for a NAND. A and B, the output is then inverted to give me Z. That's the NAND gate. Just like with the international symbol for the NOT, we had the little triangle on the end. Here we have our international and we've got the small triangle doing the same thing as the bubble, converting my AND gate into a NAND gate. And we can express it directly like we've seen in our previous slide deck. I've got A and B all knotted in order to get an output X. Same thing goes with NOR. NOR is just a combination of N for NOT and then OR to create NOR gate. I have an OR. If A and B are true, that would give me a true. Sorry, A or B would be a true, but I have to invert it because of the bubble and then make it a false. So it's an OR gate with a built-in inverter. These not as common. They're not as quick, not as easy to make as NAND gates. So the technology is virtually exclusively NOR. Even when I buy a NOR gate, it's actually made up of a bunch of NAND gates to replicate the performance of a NOR gate. The symbol, I take that greater than equal to 1 symbol in the square box that I use internationally and just put the triangle on to indicate that I'm going to invert that output to create A or B all knotted to give me X, gives me a NOR gate. So it's exercise 1. Exercise 1, we're going to start by completing the truth tables for the NAND and NOR gates. So what I'm going to first do is this NAND gate, but I'm actually going to draw an extra column here. I'm going to just create an AND. Okay, so if my input's 0 and 0, ANDed together would be a 0. 0 and 1 would be a 0. 1 and 0. 0, 1 and 1 is 1. That's just the AND. Now the NAND is the AND inverted. So I'll take this column to the left and just recreate it in the outputs to the right, inverted 1, 1, 1, 0. Okay, so baby steps to get there. I created an additional column, an AND column, an intermediate column, and solved the truth table. I'm going to do the same again for NOR. I'm going to create just a temporary OR column. 0 and 0 equals 0. 0 and 1 give me 1. 1 and 0 give me 1. 1, sorry, 1 or 0 gives me 1. 1 or 1 gives me 1. Inverted to a NOR, the 0 becomes 1 and the 1s all become 0s. So there we have the truth tables for the NAND and the NOR gates. Interesting exercise here. Turn the NAND and NOR gates into an inverter. Now when I buy a microchip, this piece of plastic packaging that's going to have several leads on it. Okay, I'm going to have power for one of them. I'm going to have ground on another, or common. And it's going to have a bunch of chips on it. So I'm just going to draw a representation of one of them. In NAND, it's going to have 2 inputs and an output. As you can see, I've got room for 4 of those on this chip. Okay, so say I've used 3. 1's already been used, 2's already been used, 3's already been used. I've got 4th one left over. I'm designing an electronic circuit and I need an inverter. Now I'm a cheap sod, okay? I don't want to spend that extra 2 cents on the chip. I don't want to spend the extra real estate on my PCB. I'm going to make 40 million of these times 2 cents. Yeah, that's a pretty nice vacation. I think I don't want to buy the extra chip. I want to design this using this leftover NAND, okay, instead of using another chip with an inverter on it. So how would I design that? Okay, here's the question. How do I design that? Well, if I look at the truth table, okay, I've got a truth table for a NOT. That's what I am trying to replicate. I have an input of a 0, the output would be a 1. An input of 1, the output would be a 0. Fairly simple truth table. But all I've got available is this NAND. It's a 2-input device. I've got a 0, 0. 0 and 0 would give me 0 for an AND. Inverted would be a 1. I could have a 0 and a 1 as an input. 0 and 1 as an AND would give me a 0. You can invert it, that would give me a 1. I have a 1 and a 0. That's going to be a 1. A 1 and a 1 is going to be a 0. So there's my true truth tables. I want to take this and use the logic out of that on my NAND. Okay. So what I'm saying is that wherever I've got a 0, I want a 1, and wherever I've got a 1, I've got a 0. My NOT doesn't have the options for 0s and 1s, so I really don't want this. How do I do that? Well, if I just tie it together. There's my input and my output. I have, say, A coming in to my gate. I've tied the 2 together and I've created an inverter. Remember I said these are universal gates. I can do all my logic simply with NANDs. Just got to get a little creative about it. Okay, they're quick, they're cheap, they're plentiful, so we want to use them. So this is a simple method of showing you the very basic operation of converting a NAND gate into simply an inverter. Let's do a timing diagram. Yeah, I'll work my way through a timing diagram for this one. I've got A and B all knotted to give me Z. So how am I going to do this? I'm going to go back to my baby steps I talked about last time. First of all, I want to know where there's a transition. Everywhere there was a transition, the output could change. The only place an output should change is where there is a transition. So I'm just going to mark off my transition lines. Baby step, really small baby step. Let's write what the values are. That should have been a 0. That was a 0. That's a 0. B. Okay. Another baby step. I'm not going to just NAND it. I'm going to AND it in the middle, okay? Let's just AND it in the middle there. I'm going to say this intermediate step, I've got a 0 and a 0, a 0, a 0 and a 1 is 0, a 1 and a 1 is a 1, back down to a 0, a 0, a 0, a 1, 0, 0. That's A and B. But Z is inverted, so I can quickly invert this and say, oh, wherever I've had a 0, I've now got a 1. Wherever I had a 1, there's now a 0. And assuming I was paying attention, I've quickly made my timing diagram output. Okay. As you do this more and more, of course, you don't have to do all these baby steps. You can just start building them very quickly. For most of you, this is the first time you've seen this, so I'm going right back to the very, very small steps on how to create, in this case, a timing diagram. I'm going to leave this timing diagram for you since I talked way too much in the first half hour. Okay, draw the gate logic for the Boolean expression. Okay, this looks very similar to something we did earlier, except we're now talking about using NANDs and NORs. Okay, previously I would have said, okay, I'm going to start at the X and I'm going to do an inversion. Here's my output. I'm only going to put a bubble down. I'm not going to do the triangle. I'm going to put the bubble down for my inversion, and then I've got the OR attached directly to it. I've got 2 inputs. First input, oh, there's an inversion. There's my bubble. And it's A and B together. Same with my second one. There's a bubble. I've got a AND again with C and D. Okay, so I could have done it as we've done it with the previous set of exercises with a whole bunch of inverters, but this time we've learned about NANDs and NORs, so I'm just going to use NANDs and NORs in order to create the answer to this exercise.
There's no D in that one, Chris.
D, sorry, it's a B and a C. You're absolutely right. Me rushing ahead. Let's make our lives easier. B, C. Good catch, thank you. Draw the truth table. Draw the truth table. So I'm just going to start my traditional way with drawing a truth table without even looking at the equation. I've got 3 inputs. 2 to the 3 equals 8. So I need A, B, and C. My truth table. I've got some unknown output. I'll just give it X. I've got 8 inputs. Half of 8 is 4, so 4 zeros, 4 ones. Half of that is 2, 0, 0, 1, 1, 0, 0, 1, 1. Quickly assembling my truth table without even really looking at it. And an output of X. Baby steps, Chris, baby steps. Let's not do directly to X. Let's do a whole lot of baby steps along the way. We're going to learn a lot more. So let's have a look here. I've got A and B. A and B. Then we NOT it. We've also got B and C, which also gets NOTed. They then get ORed together. So BC. And then we invert all that again to get our output X. So baby steps. So if I look at AB, okay, wherever there is 2 ones, I can say there's a 1 down here, down near the bottom. I got a couple of 1s. Everything else is going to be zeros. To invert it though, I just change those zeros to 1s, change the 1s to zeros. B and C, where are B and C both 1? There's 1 there, and there's 1 there. Everything else is 0. I'm going to NOT them, invert those zeros to 1s. Now I want to OR together these 2 columns. Let's OR them together. Wherever there's a 1 in either of these columns, we're going to have a 1, 0. And the last thing we needed to do is this NOT. So we'll invert that. And my truth table is correct, complete. Okay. So what do we get there? We have a truth table where the output is only true if A, B, and C are true, which is not what we had written down. Okay. But it's still correct. It's like if I was to ask you, what equals 8? You could say 4 plus 4, 16 minus 8. Okay, there's lots of ways of getting there. It's the same in Boolean logic. There's often lots of ways of getting there. What we want to do often is the simplest way, the cheapest way. Okay, the one that is quick and cheap, one that's effective, value for money. So from exercise 5b, we get to exercise 5c, draw a single gate to replace that. So we use the truth table, but we can see from our truth table that A and B and C was the only thing that equaled X. A and B and C equals X. Drawing the single gate. Which is to be something like that. So I'm going to give you a hint here how to simplify. That didn't want to happen. We want to simplify. If I break a NOT bar, say this one, I break it into 2 NOT bars. The symbol under it changes from an OR to an AND, or an AND to an OR. Okay. This is just a shortcut. So I could rewrite that expression. AB with 2 bars over it, or BC with 2 bars over it. Because I broke the bar and changed the symbol. Now if you invert something and then invert it again, it goes back to its original state. So 2 NOT bars will cancel each other out. Okay. Now we saw when we did our little inversion exercise, B and B. What does B and B equal? Let's have a look at that. If B and B are both 0, they're going to equal 0. B and B equal 1, they're going to equal 1. B equals B. 0 and 0 equals 0, 1 and 1 equals 1. So B and B equal B. That means I can eliminate a B. A, B, C equals X. Okay. So here's the proof. Well, no, it's not the proof. The truth table to me is always my proof. I keep going back to my truth table. But my truth table proves this theory, that if I break a bar above, I can change the symbol below, and it's equivalent. It's still the same. If I look at this example at the very bottom, I've got AB and CD. AB and CD. 2 bars above it, it's still exactly the same. It's still technically correct. If I break one of those bars, I need to change the AND to an OR. Still technically correct. It doesn't matter where I broke it. If I broke the bar over here, okay, because it's ABCD, I can get this. Okay. So this is a powerful tool for simplifying. Okay, we're not going to really do much on this, but this is probably the hardest part of designing electronic circuits. I have Boolean logic, lots and lots of Boolean logic, and I want to simplify it down to an equivalent that is quicker and cheaper and more effective, less opportunities for mistake. Talking about NANDs. Okay, if someone can answer me this, describe the function of an AND gate with the term, if any input is what, the output will be what. If any input is high, what will the output be? Well, that doesn't work. We need to have, if any input is low, the output will be high. Going back to our truth table. Okay, if any input was low, our output was high for our NAND gate. Okay. The next exercise I'm going to leave for you. It will take a bit of time to work through, but it's just the same sort of process that we used for the work exercise we've already done from the tank farm. Okay, read it, understand it, read each sentence very carefully, identify the inputs, identify the outputs, create the Boolean, simplify the Boolean, and then draw the gate logic. Okay, so I'll leave that for you to do on your own. I'm going to move quickly into the next one so we get this done on time. Slide deck 1.7. So we're going to look at 2 more gates. Okay, this completes our look at logic gates. 2 more gates, XOR or XNOR. Those X's could be replaced by E's, E for exclusive or X for exclusive. North America, we tend to use X's. In Europe, we tend to use E's to describe these gates. Let's have a look at why we have this specialized gate. You know, there's times I don't care necessarily about the score, the result. I just need to know if things are equal. Let's take, for example, a hockey game. The Oilers are in town, they're playing the Flames. And at the end of the 3rd period, the score is 3-3. What happens? Well, we've got overtime. That's going to kick off a series of events that need to happen for overtime. we're going to quickly scrape the ice with the Zamboni. Okay, that needs to happen. There's going to be a rush on beer sales. Better make sure we've got people there to sell them beer. There's usually a rush to the washroom. Better make sure the custodial staff are there to clean up any messes. It's going to be very busy, high traffic. And then there's what happens to the teams. They're going to do a quick discussion, how they're going to quickly get through this overtime. If it's only 5 minutes of overtime in the regular season, we're going to do what to make sure we don't drop the point, or if we can, get that second point. Okay, so sorry, we don't drop the point anymore with an NHL. You've got that point guaranteed. We're looking for that second point. However, if the score is 2-2, oh, it's the same reaction. It's 3-3. We're going to overtime. It didn't matter what the score was. What mattered was the score was the same. Now, the Oilers have lost like they should, and the score is 4-2. At the end of the third period, well, we've got a different set of things we're going to be doing. Okay, the Flames have just won. There's going to be a lot of people who want to buy Flames jerseys, so let's put an extra couple of people in Fan Addict, sell some more stuff to them. We're not selling any more beer, so those people should be cleaning up. Oh, we need security to help guide everyone back to their vehicles and off to the train. Okay. It's a totally different set of responses because the scores were different. Didn't matter if they won 6-4. Didn't matter if they lost 5-7. The response is generally going to be the same. So all we're interested in are two things equal, and we do this all the time in our processes. So let's have a look here. What are we going to do? We're going to create what's called an exclusive OR. If I look at this exclusive OR on the left, it's the symbol for the exclusive OR. It's an OR with this extra line behind it. We're going to be exclusive. It's only if A or B are true that the output is true. If A and B are both true, then it's not exclusive, okay? The output's not going to be true. So if I look at my truth table, if A or B are true, and only if one of them is true, the output is going to be true. If A or B is false, or if both the inputs are true, the output is going to be false. So we have here, if it's the same, both the inputs are the same, the output is going to be false. If one input is high and one input is low, the output is true, an exclusive OR. Below that, we have this symbol for exclusive OR. It's a circle with a cross in it. Lovely little symbol that I can find nowhere on my keyboard. Okay, exclusive OR. The international symbol equals 1. Okay, a little confusing. Okay, I've got to have 1, 1 in that little box, and I get an exclusive OR. Now, much like I did with an AND and NOT, so I can invert the output of this exclusive OR. And that gives me exclusive NOR, XNOR. So I take my truth table for my exclusive ORs, and I just invert the output. So wherever something was the same, before I had a 0, the two inputs are the same. Now I have two inputs the same, give me a 1. Two inputs that are different, give me a 0. We don't have a special symbol for this. We take the exclusive OR, and we put a big NOT over the whole statement. Okay, just like on the European symbols, we put the little triangle there to indicate something's a NOT. There's a triangle after the equals 1. On my North American symbol, my exclusive OR with a bubble after it, that's giving my symbol for my exclusive NOR. So these are things that I'm going to use where I just want to know if something's different or the same. So this little exercise here, what would we have? Who have I got here? Who haven't I called upon? Ralph. Comparator exercise number 1. I've got a 1 with an exclusive OR, exclusive NOR, of inputs for 1 and 1. It's actually let's actually broadcast this and do this on the whiteboard, make it a little bit clearer. We've got a 1 or a 1. That would be generally with an OR. If it was OR, we'd say, yes, that's true.
Yeah.
Wouldn't we? But it's exclusive. So it would be false.
Yep.
but then we've got a bubble, so it's a true.
Oh, I see.
Okay?
Yeah.
Okay, so 1 or 1 would have been a 1, but it's not exclusive here. Therefore, that would be a 0.
Yeah.
But we have a little bubble on the end, so it's a not, so that makes it back to a 1 again. Okay, so it's a little more complicated than just doing it visually. 0, exclusive NOR 0.
It's gonna be. It's gonna be. It's gonna be 1.
1, yeah. I got 0 or 0. It's going to be 0. Okay. There's no exclusive about it. There's no 1s in there. Okay. I've got an inverter to make it a 1. And then 1 and 1 exclusive NOR 1. We've already done that.
Yeah.
Okay. I've got an and 1 and 1 and 1. Give me a 1.
1.
Okay. So you got to break it down into these baby steps again in order to be able to solve these. I'm going to leave exercise 2 and 3 and 4 for you guys to do on your own. Leave that for you guys to do on your own, I think. Or have I got, no, I've actually got something here to describe what we're doing. I've got a signal. Okay, signal A. It's coming in. And I want to choose an appropriate gate such that the output X will appear. While the inverter is held low, the signal passes through my gate. When my inverter goes high, my signal through my gate is inverted. Okay, just choose an appropriate XOR, XNOR to do that. It's going to take a little bit of work. It's a good one to go and do offline. The other one I have is the signal is already being inverted. Okay, my inverter is actually in a reverse logic. It's a not invert. This is really, really common in electronics. Very common for my not controls to be inverted. Okay, this makes it a lot safer. The default of a failure is usually it's going to fail in a safe mode. So this is very common to do, to have a not on one of my control signals. So while I'm not inverting my not invert, okay, the signal is being inverted. So A is turning into X. The signal is being inverted. But as soon as I change my not invert to a 1, my signal is no longer being inverted. Okay, so go through and do a little bit of work with your truth table, do a little bit of work with this timing diagram, take a whole bunch of baby steps, and decide for each of these cases if it should be an exclusive OR or an exclusive NOR that would do the task for you. I mentioned buffers about 2.5 hours ago. A buffer is there to deal with variation. Nothing we make is perfect. Okay, so if I'm just going to open up my whiteboard again. Say I have a timing diagram and I've got an input A. Now the reality is they're not usually nice square waves. Okay, real world, an ugly wave. And I've got a B. So real world, let's draw some lines showing where changes occur. So I've got this change at A, this change at B. Oh, they're actually not quite aligned. There's a small variation. And then I'm going to do my output. I'm just going to do A and B. Well, it wouldn't actually change right on that line. Okay? That's not realistic. The output's not going to change straight away. There's going to be a small delay. Okay, there's going to be a small delay. So let's change that. There's going to be a small delay before it moves. Oh, and once again, a small delay. Where's that going to go? Who knows? Now, imagine, not only do I have this problem, but A, that signal A, that's coming from a tank farm 100 meters away. There's going to be a small delay in that signal arriving. So that would offset my AB a little bit as well, wouldn't it? I get all these timing issues in the real world. It gets messy. It causes me a lot of problems. So what I really want to do is I want to save A. A arrives, B arrives, and I want to transition at the same time. So I create a buffer. Now the buffer actually gets another signal to say, okay, your zeros and your ones, whatever it is, you only read them when I tell you to, and you transition when I tell you to. Okay, so if A arrives a little bit later, okay, than B, it doesn't matter. On a timeline, you don't release until I tell you at exactly the same time. Okay, so therefore B and A will change at approximately the same time. This is what buffering does for us on a control system on the input. We also buffer our outputs. We do this all the time with our music. Okay, when you're downloading a YouTube, we're buffering. We're downloading extra data. There's way more data coming down than we'd be able to watch at the speed we're receiving that data. We want to play it back at a reasonable speed. So we buffer that data. At the bit level, we want to really do this for our inputs and our outputs so we get better control. So this is what a buffer is used for. Let's go back to my slide deck for buffers. So I need to deal with the real world aspect, the variation in performance. Okay, and we do this with a buffer. Sensitive digital electronics also need protection from static discharge. We talked about ESD when we talked about basic electric theory, discharge shocks. We need to protect it from other factors. Buffers can often do that as well. Buffers, drivers, what they do is they ensure there's a good electrical interface with our system so that we run as expected. A buffer is basically just an identity. It holds it and then reproduces at the appropriate time. It's kind of like the smallest bit of memory you can have to hold a little bit of information and release it in a timely aspect. Okay, we can draw those with triangles as I did there. Some buffers invert. They invert on the way in and invert on the way out. They're actually cheaper to make than a buffer as I've drawn. Even though we use the one on the right, we tend to use this one on the left symbol, even though in the practical application we're double inverting. So exercise 6 I have here. Create truth tables for these two circuits. Let's go ahead and do that. I think I've got this on the slide deck. It's all complete except for this last piece. Okay, so if I created my truth table for my big nasty circuit, and I create my truth table for my second circuit, I'm going to get the same thing. Okay, to me that is my proof. Okay, but I can also do another proof this way. What I've got here is A, B, ORed, okay, exclusive ORed, and then inverted. that's what we call the short form. Okay, the short form of the exclusive NOR. This AB, or for to say in English, A not, B not, or nodded, that would be considered the long form of an exclusive NOR. And I've seen people write this down because, hey, it's on a keyboard and this exclusive NOR symbol does not exist on my keyboard. In fact, when I go through all my symbols, the thousands of symbols available in the background, it doesn't seem to exist there either. Can't find it in any mathematical routines that Word has or Excel has. It's kind of a unique symbol to have. So people often write things out in the long form because they can. So A, B, or A prime, B prime, primed. Long form of the exclusive NOR. I should point that out because those are quiz questions. Prove that these circuits are equivalent. Okay, so remember I said that NANDs are what we rarely use in electronics. Okay, even though I might buy an electronic chip and it's got a symbol for a NOR, and it tells me that there's four OR gates on there. The reality is, at the silicon level, each one of those is made with 3 NANDs. Okay, so how do I prove that these are equivalent? I go back to my truth tables. So to prove those, create the truth tables for both circuits, and you'll see that X equals Z, and that is my proof that they're equivalent to. Let's have a look at this gate. Okay, once again, this is a real-world item built up of NAND gates. How would I create this or solve this? What single gate is it equivalent to? Well, if I look AB, if AB is 0, 0, would be a 0, inverted would be a 1. Okay, etc., etc. If I go through and solve this, you're going to find out that it is equivalent to one of the gates we've discussed today. This is real world. This is really how we build that gate. Even though it looks on paper to be a lot more complex, okay, it is cheap, it is fast, and I can make them with very high quality with very little effort to do it this way. Okay, so going back to the universal gate, the NAND gate, that is usually what we make up most of our electronics with in the real world. Any questions? Any questions?
I got a question.
Sure, go for it.
Do you know any cool resources where we could just do like a lot of ton of practice that will help us familiarize?
What a great question. Did I pay you to lead into this next slide?
Oh, okay.
So follow this link here. Okay, now it's a little kludgy. It's free. Okay. I've never actually tried it on an Apple, but this is a great thing to put together everything we've done today and tons more. Like this one here, there's a slot machine built right into this program, and all the stuff. You can build your own circuits and test them. Use switches to change from high and low for your inputs, high and low. Okay, so if you go through to this multimeter link, it's here in the slide deck. It's also directly out of section 1 under content, a link to this, and you can play with this, do all this sort of stuff that we would otherwise do in a lab if we had the equipment here online. Okay. Kahoot. How many of you used a Kahoot before?
Yeah.
Yeah. Yep. Okay, let's have a quick little quiz. For those of you who have not, pull out your smartphone and go to www.kahoot, not Cahoots, not an S, .it for Italy. okay, and log in, and then it's going to ask you for a game number, okay, a game pin. And I will give you that pin, and then you can enter and put your name in. And we've got a little quiz here with 10 questions. We'll see if anyone has learned anything in the last few minutes or 3 hours, okay? So I am going to screen share, exit. I hate this music. Okay, so there's the game pin that you'll need to enter, 686-8534. So how this works for those who have not used a Kahoot before, there's going to be, I think I've put 10 questions into this quiz, and you get marks for getting it right. You get more marks for getting it right quickly. So say there's 1,000 points, and you get it right straight away, you get the full 1,000 points. The longer it takes you to answer and get the correct answer, the less points you have. You only get one attempt at answering. If you hit the wrong thing too early, you're
You can
stuck
turn
with
off
it.
the music if you'd like with that little music icon.
I just want to turn it off.
Hit the one below it. There you go.
Can you still hear me? Can you still hear me?
Yep.
Yeah.
Okay, I just wasn't sure if that shut off me as well.
No, you're good.
Okay. We've got 26 people logged in. And that means I'm still waiting for one. Maybe one person hasn't done this before or is struggling with it. Maybe one person's gone to the washroom and didn't hear us start this thing. But I am going to start with what we've got here. Okay. So, MECH 25, 205 logic quizzes, we're underway. First question. This is the symbol for what logic gate? So on your phone, press the appropriate color and shape. It won't have the options written there, believe it. 8 seconds, 7 seconds, 6 seconds, 5 seconds. Keep going. Take a wild guess now. Okay. 13 of you got a NOR gate. Only about 50%. That's not great. I would have expected better out of that. Let's move on to the second question. Seth, Jacob, Anch, Taylor, and Cody were fairly quick. Second question. Which equation is correct for this gate? Which one of these equations? Excellent. Way better than the previous question. 18. Good. Did our leaderboard change a little bit? Yes, it did. Some people were way quicker. Next question. What is the Boolean equation for this gate logic? 30 seconds because it's a bit harder, this question. Someone's already got it. Did they guess, or did they see the shortcut? Now 20 people are saying, what's the shortcut? Seven of you got it. The shortcut was to follow the C. If you followed the C, you could quickly eliminate the others. Okay. Oh, Mac jumps into the lead from nowhere. He's on fire. Is he 3 in a row? What is the correct Boolean expression for this gate logic? good, excellent. It's not easy to get. Max stays in the lead. What is the correct Boolean expression for this truth table? Okay, looking at the truth table, what's the correct Boolean expression? Whoa. Look carefully at your truth table. Okay, I think a lot of you may not have been comfortable with that last answer because C is not there. In this case, C is a don't care. Okay, and this is one of those cases where I'd say, I'd go back to the client and say, hey, you told me these are the inputs, but one of these inputs just doesn't get used. It's a don't care. It's kind of an expensive thing, but this is what the truth table would have told me. Okay, so the answer was actually A, B, or not it. Next question. What gate is this timing diagram for? So this is not written in my traditional way to demonstrate it. This is a real world situation. I've got an A and B in signal, an A and a B signal, and I've got an X output. And I'm trying to work out what sort of gate it is. What sort of gate will give me that result? And most of you got it good and all. Max staying ahead. Which logic gate best represents this timing diagram? Excellent. No, not excellent. Only 2 of you. I looked at the big 12 and thought, yeah, you guys are right, but no, you're wrong. Only 2 of you got it. This is going to be tough. We've got a top score of only 4,500 so far. And went to question 8. The value of X. What's the value of X? Value of X. Oh my goodness, 50-50 split. Guess I'm going to have to reuse some of these questions. Value of X on this one is excellent. Last question. Value of X. 20 seconds. It's a little more complicated. Whoa, a lot more complicated. Let's see how we did at the end. Alex wins, 4,600. Nope, Alex third, sorry. Mac, 5,200. 8 out of 10 goes to Seth. Well done. Now, this is the first time I've done a Kahoots remotely. I'm not sure how the timing works at your end, but it looks like 8 out of 10. Must have been enough timing for it to be able to do the quiz. Okay, that's all I have for today. If you've got any questions, email me. I see it's 9 minutes to your next class. Email me. I'm so responding at the moment. I've got a ton of email and other stuff that I'm doing, but I will try to get back to you. If you email me today, I should get back to you by the end of the weekend. Okay, so that's all I have today. Enjoy the rest of your day and have a good weekend.